We have already seen and used this first rule of logs, that if I have the log of something to a power, I can bring that power down and it becomes a coefficient. This rule, and in fact all of these rules, are true for the log with any base, any legitimate base, so a positive number other than 1. I've just written them out for the natural log because that's the one that we're going to use most often. Okay. The rules we haven't used are these product and quotient rules. And I think the key for remembering them is simply to remember that log means exponent. So if a was e cubed, that just means that the natural log of a is 3. Log means exponent. The exponent that gives me a is 3. And I know my base is e because it's the natural log, which is the log base e. If b was e squared, that just means that the natural log of b is 2. Now, ab would be e cubed times e squared. And I know that when I'm multiplying exponential expressions with the same base, I add the exponents. That would be e to the 3 plus 2, which would be e to the 5, which means the natural log of ab, the exponent that gives me ab, is what I just calculated, 3 plus 2, or 5. It's the sum of the logs for the individual factors. So log means exponent. If I'm adding logs, I'm adding exponents. I add exponents when I'm multiplying. The quotient rule is similar. Log means exponent. If I'm subtracting logs, I'm subtracting exponents. I do that when I'm finding the exponent for a quotient. Okay, so how can those rules help us with derivatives? Well, let's suppose that I had y equals x squared tan cubed x over cosine to the 5th x. Now, that's 3 factors connected with multiplication and division. I could certainly take the derivative of this using a combination of product rule, quotient rule, and chain rule. It's been a long day. I'm not sure I feel like that. And I'm a math teacher. I think this stuff is fun. But I will admit that if you have to use too much product and quotient and chain rule in one problem, it starts to just get tedious. Okay? And this sort of suggests that logs give us a way of turning products and quotients into sums and differences. And I know that the sum and difference rule for derivatives is way easier because I just deal with each piece one at a time. Okay. The problem is I'm not allowed to take the natural log of this. I can't take the natural log of this because I'm only allowed to take the natural log of something that's positive. So I have 2 problems. Sometimes this is 0, and I can't take the natural log of 0. And sometimes this is negative. Where it's negative is actually the bigger problem, because it's going to be 0 at isolated places. Okay? Actually, for this particular one, it's only 0 if x is 0, because that makes this 0. The places that would make tangent 0 are actually not in the domain of this particular function, because if tangent... Oh no, I'm lying. I'm sorry. Those are the places that make tangent undefined. Tangent could be 0 at any multiple of pi, and then cosine would be either 1 or negative 1, so it would still be defined. Oh, my bad. Okay. But those are isolated places. There's no interval where the function's consistently 0. So chances are, if I can find a technique that works for all of the places where this isn't 0, since I'm working with a function that's continuously differentiable, if the formula is defined at the places that make it 0, it's likely that it would work there too. Not 100% guaranteed, just likely. The bigger problem is that this is sometimes negative. And it's going to be negative for whole intervals at a time. Okay. Tangent cubed is going to be negative whenever tangent is negative. Okay. And tangent's negative for any angle in quadrants 2 or 4. Cosine to the 5th will be negative anytime cosine is negative, which would be in quadrants 2 or 3. Now, if x corresponds to an angle in quadrant 2, both of these factors are negative. Those negatives would cancel, but that doesn't really help me out because I'm wanting to use the rules of logs to separate those factors. And if I need to keep them together to keep things positive, then I'm not allowed to separate them because the individual pieces are negative. So the fact that this is sometimes negative is a problem that I can't avoid, but it is a problem I can fix. I have fixed it. Now it's never negative because the absolute value doesn't give me a negative. Now I've changed it, but I had an equation and I changed both sides, so that's legal. Okay. That does not solve the problem that this is sometimes 0. In fact, this function is 0 at any multiple of pi. Okay. So I'm just going to make a note that our result may or may not be valid if y is equal to 0. But we're going to come back once we've finished this process and revisit that issue. But let's just make that note and keep that in the back of our mind. But I'm okay going forward because it's only 0 at isolated places, never on a consistent interval. Okay. Now, because it's never negative, and temporarily just ignoring the possibility of it being 0, I'm allowed to take the natural log. But before I do that, I'm going to simplify even more. Because I know that I'm going to want to use the rules of logs to separate these pieces. So I want each piece to not be negative. Fortunately, absolute values distribute over multiplication and division. They don't distribute over addition and subtraction, but they do distribute over multiplication and division. So I can say this is the absolute value of x squared, absolute value of tan cubed x, absolute value of cosine to the 5th x. Now you might say, do I really need that absolute value because x squared is not negative? That's true. But I'm going to try to use my rules of logs to simplify things as much as I can. And I'd like to be able to use this power rule to simplify things. And it turns out the absolute value of x squared is the same as the absolute value of x squared. Absolute value of tangent cubed x is the absolute value of tangent cubed. Okay. If the absolute value is doing anything, it's just changing the sign. Okay. So we're taking a power and evaluating the absolute value. It does not matter what order I do that in. Okay. So we can do things like so. Once I've done that, taken the absolute value of each side, distributed the absolute value to each factor, and for each factor that was a power, applied the absolute value to the base. Now I'm going to take the natural log of both sides. So now we can use our rules of logs to try to simplify this. So the natural log of the absolute value of y, this is a quotient. So we'll get the natural log of the top, which was the absolute value of x squared, absolute value of tangent of x cubed, minus the natural log of the bottom, natural log of the absolute value of cosine x to the 5th. Here, this was a product, so I can break that up into a sum. Natural log of the absolute value of x squared plus the natural log of the absolute value of tangent of x cubed minus the natural log of the absolute value of cosine x to the 5th. Now, usually, when I use these rules, I'm not going to do it in 2 steps. Here, first step was quotient rule, second step was product rule. But notice, the 2 factors that were on top, I ended up with a positive copy of their log. The factor that was on bottom, I ended up with a negative copy of that log. And even if I'd had other factors on bottom, I would have distributed the negative sign that applied to the entire bottom. So any factor on bottom, I'm going to be just subtracting the log that corresponds to that factor. Okay, excellent. Now, we're ready to take the derivative. Let me just copy this at the top of the board. Natural log absolute value of y, natural log absolute value of x squared plus natural log absolute value of tan x cubed minus natural log absolute value of cosine x to the 5th. Oh, and I'm actually not quite ready to take the derivative. I've got one more rule of logs that I can apply. I can apply my power rule. Okay. So I can say this is 2 natural log absolute value of x plus 3 natural log of absolute value of tan x minus 5 natural log absolute value of cosine x. Okay, and oh, I'm sorry. This left-hand side was the natural log of the absolute value of y, not of x. Okay, now we're ready to take the derivative. So the derivative of the natural log of the absolute value of y is the derivative of this whole thing. 2 ln absolute value of x plus 3 ln absolute value of tan x minus 5 ln absolute value of cosine x. Now, here I need to remember, this is super important, that we showed that the derivative of the natural log of the absolute value of x, even though that's a composition, we worked it out using, by writing it actually as a piecewise function, and we got that there's just one formula for that result. It's 1 over x. That's not just the derivative of the natural log part, that's the derivative of the natural log of the absolute value. So, while the absolute values were necessary in order for me to be able to take the log in the first place, they're going to drop out when we take the derivative. So here, I'm going to get 1 over y. That's the derivative of the natural log of the absolute value. That takes care of both parts. It's still chain rule because I'm taking the derivative with respect to x of a function of y, so we multiply by the derivative of the inside part, which is y prime. This is going to equal 2 times the derivative of the natural log of x is 1 over x, plus 3 times the derivative of the natural log of tan x, natural log of absolute value of tan x is 1 over tan x. That takes care of the log and the absolute value. Chain rule, because the inside part is tangent, we multiply by the derivative of tangent. Minus 5, the derivative of the natural log of the absolute value of cosine is the reciprocal of cosine. Chain rule times the derivative of cosine. All right, so this is 2 over x plus 3 over tan x, and the derivative of tangent is secant squared. I'm just going to write that on the top of that fraction. And then this is minus 5 over cosine x. Derivative of cosine is negative sign. That negative, combine with that to make it a positive, and then a sine x. If I want to, I could rewrite this sine over cosine as tangent, or I can keep it as sine over cosine. Either way is fine. Okay. But this was 1 over y prime. I want to solve for y prime, so I'm going to multiply both sides by y. Okay. So, when I do that, I will get y prime is equal to 2 over x plus 3 secant squared x over tan x plus 5. I think I am going to go ahead and just write that as tangent of x. And then times y, where y was x squared. Oh dear, what was y? Tangent cubed x over cosine to the 5th x. That is my formula. That is valid anywhere it's defined where the original y value isn't 0. Okay. Now, the original y value would have been 0 if x was 0 or if tangent was 0. Notice, though, I'm multiplying through here by an x squared, which can cancel with that x, and a tangent cubed x, which cancels with that tangent of x. So while it's not the case that 0 over 0 simplifies to 1, if I do allow myself to cancel those x's and those tangents, I'm probably going to get the formula that I would have gotten using product, quotient, and chain rule. So certainly this version is still undefined if x or tangent of x is 0. But if I do the multiplication and cancel that out, because the only reason these ended up in the denominator was because I did this illegal taking the natural log thing in the first place. If I allow myself to cancel them, I'm probably going to get the formula that does work even if they are 0. Now, I'm going to just go with the caveat that the result may or may not be 0 if the original function was 0. But this definitely gives me a formula that works anywhere where it was non-zero, and likely simplifies to something that works if it was 0, if the function is differentiable there. Okay. So, let's end this video here, and then we'll talk a little bit more about this.